Now let's try an example. Find the slope of the tangent line to the curve y is equal to f of x, which is equal to x squared, at the point 1, 1. So x is 1, y is 1. This is the rule we want to use, the rule that was just mentioned. So the slope of the tangent line is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So what you want to first do is look at what a is. A is your x value. So you can substitute that term, that value, into the rule. So we can look at this as the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Now we have a function that you're placing these x values into in order to get your solution, and that's right here. But we also know what f of 1 is because that's from over here. So f of 1 plus h means f of 1 plus h is equal to 1 plus h, the whole quantity squared. Let's write that out. I'm going to put it on the side here because I want to keep this as my workspace for the limit. So what I usually do is anything that I want to figure out on the side before I substitute it into the formula, I make sure I have a separate workspace for it. So f of 1 plus h is 1 plus h squared. Where did I get that again? F of x is x squared. So that means whatever you're placing into this function notation, f of 1 would have been 1 squared. F of 2 is 2 squared. So f of 1 plus h is the whole quantity 1 plus h squared. You have to FOIL it. Do not say it's 1 squared plus h squared because that's wrong. Make sure you FOIL it. So this becomes 1 plus h times 1 plus h. When you FOIL it, you get 1 plus 1h plus 1h plus h squared, which is 1 plus 2h plus h squared. That trinomial is what you're substituting into this term here. So we write this now as the limit as h approaches 0 of 1 plus 2h plus h squared. Now what about f of 1? F of 1 right here. F of 1 is 1. Remember, that's function notation. This is your x value. When x is 1, y is 1. Or you could just plug it right in here. F of 1 is 1 squared, which is 1. So right here, minus 1 all over h. Now we've seen these questions. So this substitution, this manipulation of terms should not be new. So we look to see what can be simplified. 1 minus 1 is 0. So I have limit as h approaches 0 of 2h plus h squared all over h. Do not cross out the h's. You need to factor out an h from the numerator because remember, you can only simplify if you have factors. So we think of this as the limit as h approaches 0 of h 2 plus h all over h. Now you can simplify. Limit as h approaches 0 of 2 plus h is 2 plus 0, and that's 2. So right here at this step is where I actually evaluate the limit. And then I substitute the 0 in for h, and I get the slope of the tangent line to the curve y is equal to f of x, which is x squared, at the point 1, 1 is 2. So again, what we just found here is the slope of the tangent line at 1, 1. The slope of the tangent line, that's what you're finding. This rule here finds you the slope of the tangent line. This rule here finds you the slope of the tangent line. So make sure you know that. Make sure you say, okay, highlight that slope of tangent line. And that's right here, this rule. Now this rule that we just worked with, that gave us the slope of a tangent line to a curve at a point, is also known as the derivative. So here's our formal definition for a derivative. The derivative of a function f is the function denoted f prime. That's how we call this, is f with that little 1 on top is called f prime. It's defined by f prime of x, so notice this prime on top here, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, which is equal to the limit as z approaches x of f of z minus f of x all over z minus x. Now this looks a little different than the rule from before, because before instead of x they had a. But lots of times you're not going to be x to find at a specific point. Like they give you the a value, the xy value, they won't give you a comma f of a. They'll just give you a function f of x and say find the derivative and keep it in terms of x. In that case, you're using this rule. So this is extremely important. Extremely important. The second piece to the rule is the difference quotient right here. This here is called the difference quotient. So what that just means is as z approaches x, f of z minus f of x all over z minus x, what you can say is the derivative is the limit of the difference quotient. And this is all true provided that this limit doesn't exist. So in order for this to be true, you have to be able to evaluate that limit. And we say that if a function does have a result of such, we say that it's differentiable at a point A. Differentiable is the key word here, differentiable at a point. And this process is called differentiation. Differentiation. So notice a few new keywords here: derivative, differentiable, differentiation. And they all mean taking a derivative of a function. So let's look at an example. Find the derivative of f if f of x is equal to x squared. Now notice it's the same function from before where you were x to find the slope of a tangent line. So you were x before to find the slope of the tangent line to the curve x squared at the point 1, 1. But notice what you're not given here. You're not given a point. You're not given 1, 1. So your x just to find the derivative. So that means you need to use the limit rule that uses the x and the f of x in there. So this is the rule you want to use. You want to use the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, yes, that this whole piece gives you the slope of a tangent line at a point, but they don't give you a specific point. So what you're finding is, what you're going to find when you substitute everything is you're going to find the general equation that will give you the slopes of the many tangent lines at all the points that could be on that curve. Because if you think about it, x squared is a parabola, right? So at any x value that you pick, what's the slope of that tangent line? Well, there's infinitely many tangent lines because there's infinitely many points on that curve. So what you're going to find here is you're going to find that equation that's going to give you the equation for your slopes of your tangent lines. So it may take a little time to start to see what we're doing here, but eventually you'll start to see that this derivative